This is a video lesson on optimizing area, and specifically in 2 dimensions. So I'll talk about what that means, and there will be another video for 3 dimensions. But the idea of optimizing area in 2-dimensional shapes is the idea of enclosing an area with a fence. So if you have a certain amount of fence that has to go around an area, that fence represents the perimeter, and the amount of space that's inside it is the area. And optimizing means that you get the most area inside the shape per the amount of perimeter that you have. And there are 4 theorems that basically say the same thing, but I'll take you through them, what they are and what they mean. The first one is that of all figures, that's just a word for 2-dimensional shapes, with the same perimeter, the figure with the most sides will have the greatest area. The conclusion of that is that if you have a choice of shape, circle has the best ratio of area to perimeter. That's because a circle essentially has infinitely many little sides. But I'll show you how this works. So I've said here that it's all shapes with the same perimeter. So the perimeter of this square, it's 10 by 10, it's 10 plus 10 plus 10 plus 10. That's a perimeter of 40. And this is a regular pentagon, 5 sides, each one 8. The perimeter is 8 plus 8 plus 8. 8 times 5 is 40. And this circle has a radius of, it's actually an irrational number, but about 6.366. And if you did 2 times pi times r, that perimeter works out to be 40 meters as well. So of all of those shapes, if I calculated the area here, the area is obviously 10 times 10, it's 100. Here I would need to know the apothem. And I wouldn't just make up an apothem. For this to be a regular pentagon, there's a specific apothem here. And I'm not going to go through the math of that, but it turns out that this area is equal to 110. It's a little bit more. Notice that there are more sides here. And this has a bigger area, even though they have the same perimeter. And this is as if it had infinitely many. And of course, I could do a 6-sided, a 7, 8, 10-sided shape as well, and you would see the progression. But if I go to circle, which is essentially the maximum number of sides possible, also for a shape that has a perimeter of 40 meters, it has the greatest area. So that's what that means. If you can choose a shape, circle's the best. If you have limited choice, the shape with more sides will have a bigger area. That's theorem 1. Theorem 2 says that of shapes that have the same perimeter and that have the same number of sides, the figure which is the most regular, the word regular in shapes means that all the sides are equal. That one will have the greatest area. So in conclusion, the conclusion of this theorem is that if you do not have the choice of number of sides, because remember that if you do, more sides is better, but if you can't choose, at least you want to make the sides as equal as possible. So for instance, if we look at this square that's the most equal, the perimeter here is 40. The perimeter of this rectangle, 12 plus 8 plus 12 plus 8, is also 40. And this rectangle, 16 plus 4 plus 16 plus 4, is also 40. You can pause and check it out if you don't believe me, but it's true. And if I look at the areas of these, the area here, 10 times 10 is 100. This area, 12 times 8 is 96, and this area is 64. So even though they all have the same perimeter, they do not all have the same area. The greatest area is the most regular. It's where all the sides are equal. And if you compare these two, this one is more regular than this one because the 2 sides are closer to one another in measurements, and that has a greater area than this one. And next, the last 2, theorems 3 and 4, are the same idea but backwards. They're saying that if figures have the same area, so rather than having the same perimeter, if I had the same area, then the figure with the most sides will be best. In this case, best means smallest perimeter. So note that greatest area and smallest perimeter essentially mean the same thing. It means we're looking for the best or ideal shape. And again, that means that if you can choose, circle is going to be the best one. So if I look at a bunch of shapes, and instead of giving you the side lengths, if I gave you the same area for each one, and I solved backwards here, I would have to solve for the side length. It would turn out to be 10, which means that the perimeter is 40. Here, if I solved, and there's, again, the math of this is not really important, but if I solved backwards here, I'd find that that was my side length, and that my perimeter would be approximately 38.12. So note that the perimeter is a little bit smaller. And if you're looking for perimeter, which is like the amount of fence you would need, you'd want it to be less. You'd want to use less fencing if you can. And finally here, the radius here works out to be, and you could find this, you just make area equal to pi r squared. You could find the r. I wrote approximately because it's an irrational number. It had lots of decimal places. And that means that the perimeter is this. It's the smallest one in the circle. Circle is the best because it has the most sides. And finally, the final theorem, also the same idea we had seen, but backwards. If you had a bunch of figures with the same area and the same number of sides, the most regular one will have the smallest perimeter, because smallest perimeter means best shape. So if you can choose, you'd want the most regular one possible. So in a case like this, if I had an equilateral, all three sides equal, triangle, area 100, what's the perimeter? The math of this one is complicated, so I want to show you how to do that, because that comes up frequently. If you want to find the side lengths of an equilateral triangle and you know the area, an equilateral triangle has the property that all interior angles are 60 degrees. And there's an area formula that you probably learned last year. That's A times B, that's side, times sine of the angle between those two sides divided by 2. My A and B I don't know. They're both x. I know that they're equal. The angle in there is 60 degrees. I know that the area is 100. So this is something that's solvable because I can multiply both sides by 2. I can divide both sides by sine 60. And then, to solve for x, I have to take the square root. So I can find that the perimeter here is going to be 15.197 plus 15.197 plus 15.197. The perimeter of that example works out to be 45.59. If you want to go back, pause, rewind, and check out how I did that math, please do. That is important. And let's say another triangle. So it's still three sides, but now they're not all equal. I'm saying that this side here is 25, and these two are equal to each other. Probably could have used a different variable. What I would have done is solved 100, the area, is equal to base 25 times height, which I don't know, divided by 2. I'd solve for that height. Here it works out to be 8. And then to find this, I would have to solve a Pythag in the half triangle where this height is 8, this length to the edge is 12.5, it's half. And I would solve a Pythag calculation to solve for that hypotenuse, and then I would add up all three sides. It turns out that the perimeter here is 54. Notice the perimeter here is bigger, 54.68, than this one, because this one is more regular, and more regular means bigger area or smaller perimeter. And finally, a more extreme example, again, I would solve 100 is equal to 8 times height divided by 2. I'd solve for height, works out to be 25. Then I do a Pythag calculation, I'd add up all the sides. Perimeter is even greater here. So the big takeaway is that if you're dealing with two-dimensional shapes, if you have the choice of the number of sides, more sides is better. Circle is the best of all. And if you do not have the choice of number of sides, the most regular possible, meaning as many sides equal and as close to each other as possible, is the best. Stay tuned for a video on three-dimensional optimization.